Hello and welcome back. Today we're going to go over the Hippo graphics pipeline, and this is really more of a theory video just to explain sort of some of the intricacies of OpenGL and how we actually get to render something on the screen, as well with what I plan to be doing with Hippo in terms of our graphics pipeline. So we talk about VBOs. These are vertex buffer objects. EBOs are element buffer objects. VAOs are vertex array objects. Meshes, shaders, and Hippo pipeline architecture. So VBO, really all it is, it's a way to store data on GPU memory, right? It's a contiguous chunk of memory. You decide what that means and how you're going to use it. So you can represent any data. For us, obviously, to represent data related to rendering, such as vertex positions, texture UVs, normals, vertex colors, etc. So when we talk about a VBO and sort of how we build it out, there's a couple of different ways that we can expose the data to OpenGL. For example, we could have a VBO, right? Which would have sort of an X position, a Y position, a Z position. This would be for the first vertex, right? Vertex 1. And then it would have sort of the X, the Y, and the Z for vertex 2. And then again, X, Y, Z for vertex 3. And you can imagine these three vertices with certain positions will give you a triangle somewhere on the screen. So if this is my vertex positions, I could have another VBO, right, with maybe an RGB value, right? So the color of vertex 1, and so on and so forth for the other vertices. So you can see I'll have two VBOs, right? One for the vertex positions and one for the vertex colors. That's what I would consider bespoke VBOs, right? So a VBO exists for a given piece of data, contextual data for the vertices. Additionally, you could also interleave them within a single VBO, right? So what does that look like? That just looks like a really big VBO that has X1, Y1, Z1, R1, G1, B1. That's all the data for the first vertex, right? So this is position and this is color. And then you have your X2, Y2, Z2, R2, G2, B2. And again, position for 2 and color 2. Right? And so what are the differences, right? Why would you want to do this over the two separate VBOs? It really comes down to sort of how the data is going to change. There's a rule of thumb, basically, and you can look at this link here, just sort of for the best practices that come from the people that actually developed these OpenGL spec in the first place. But the rule of thumb is if the data is static, put it all on a single VBO, because you only have one array sort of to fill in, and you only have one array to reference on the back end when you're trying to render. If any part of the data is dynamic, you want to pull that out into its own VBO. Basically, we can say, hey, OpenGL, let's assume here we're going to go two separate VBOs. Our positions will never change, so this will be a static. And for the colors, let's say that they are going to change, so this would be a dynamic. Oops. And so when we generate these VBOs, we can actually tell OpenGL if we expect the data to change often or not, and it will do something in the backend according to the driver in order to place the data in a spot in GPU memory where it might be faster to read from or faster to write to, right? And again, if it's static, we can put all the data, interleave it into a single VBO, and that way you only have one buffer to deal with. There's also some performance implications to doing it this way. This is meant to be faster if it's a single VBO. EBOs, it's just again another buffer. It's another contiguous piece of memory, but it's a special one. It's meant to be used to track elements. So elements, if we just look at what it might take to draw something like a square, right? Everything we draw is triangles. So there are 4 vertices, right? In order to draw this rect, you really have sort of one triangle here and one triangle here. Without elements, the way you specify how to draw something to OpenGL is you say, it's a call called GLDrawArrays. And for that, let's just name these. So this would be vertex 1, vertex 2, vertex 3, vertex 4. And OpenGL works in counterclockwise, so if you define the vertices counterclockwise, the face will be facing you. If you define it clockwise, the face will be facing away from the camera. So if we wanted to render this is two triangles back to back, we would have to give it 3 vertices for the first triangle, right? So if we're going counterclockwise, we'll say our VBO, right, will have V1, V2, V3, or sorry, V4 down here. Right, so that's the first triangle. And then the second triangle is V1, V4, V3, right? So V1, V4, V3. So if you notice, there are duplicates here, right? We have V1 twice, we have V4 twice, and then V2 and V3 are unique. So this is probably not a big deal when we're dealing with just one rect, but when you're dealing with something like a 3D mesh, you really don't want to spend the memory duplicating this line, basically. We can ensure that we don't have duplicates in here to save on that memory by using elements. And elements, they just allow us to define this. So a VBO would just have V1, V2, V3, V4, and that's it. These are the vertex positions. And then we have an EBO. Again, it's just another buffer, but it's special in OpenGL land, and it's called indices. And so this one will tell it the indices in which to render, right? So in this case, we would give it, so these are indices into this array, so we would give it 0, so 1, 2, and 4, so that's 0, 1, and 3. And then 1, 4, and 3, so that's 0, 3, and 2. Right? So V1 and V1, V2, V3, V4, and V4. And so now, instead of giving it one giant array, let's assume this is a very complicated 3D mesh, instead of giving it one giant array that takes up a lot of memory, we give it just the unique vertices, and then we just supply it with this sort of supplemental EBO. That is, these are just unsigned integers, so they're much smaller in terms of space, instead of having to define, because remember, vertex 1 is actually an x, y, and a z float, right? So this does add up, and you can see that if with an elements array, we can just give it indices into that buffer, and we can actually end up rendering this rect by only providing the 4 vertices. And the rest of this just explains basically what I just went over. So these are some of the calls you might see when we're dealing with VBOs and EBOs. So you call gen buffers, bind buffer, and buffer data. And buffer data is the call where we actually give it the data. So we generate our data. So we have the mesh data, let's say the vertex positions, and we call GL buffer data to copy that onto the GPU. And that allows us to tell it if it's static or dynamic. Now VAOs, they're just a collection of VBOs, right? A single VAO could have multiple VBOs attached, for example, the vertex and the texture, right? Texture UVs, I was using colors earlier, so this sort of system, where I have a VBO for the positions and a VBO for the colors, they might both be linked to the same VAO. And all VAO does is it caches state, right? OpenGL is a state machine, really. You define the state, and VAOs allow us to restore that state that we set it up with, right? So again, if I have 2 different meshes with completely different VBOs, I just rebind one VAO for each mesh before I render it. So these are some of the calls you'll see here. So gen vertex arrays, bind vertex array, so similar to the VBOs. And you'll see these enable and disable vertex attrib array, and this GL vertex attrib pointer. This will be very important when we deal with shaders, but we'll get to that in a bit. Let's look at meshes. So meshes, really, all they are is a compilation of data, right? It could be vertex positions with texture UVs, with normals, and all of that stuff that describes what a mesh is, right? And you've seen this, like .objs, .stls, .3ds. These are just normal 3D meshes that something like Blender or Maya would be able to export for you. And all they do, like these different formats, they have different pros and cons, but ultimately they tell you the same thing, right? They're giving you vertex information. And for us, we're going to take that vertex information and actually use it to render, right? So when I talk about meshes in the context of Hippo, it's really just going to be a class that can take some raw data. It'll make the necessary OpenGL calls and generate all of the state on the OpenGL side in order to allow us to quickly bind and unbind a mesh and have the rendering work for that mesh. Now shaders are interesting, right? Because with modern OpenGL, nothing will get rendered unless you have a shader. So we use the GLSL shader language, which is the OpenGL shader language. You have 2 main shaders, and especially 2 main shaders that we're going to work with. The vertex shader does work per vertex, and the fragment shader does work per fragment. Think like a pixel. If we just look at this triangle, for example, maybe I'll make another one bigger. There are 3 vertices, right? 1, 2, and 3. The vertex shader does work on each vertex, right? As the name implies. And then it can prepare the data for the fragment shader. There's a bunch of steps in between, but we're not going to deal with that for now. The fragment shader, usually what OpenGL does in the back end is it takes these 3 vertices, and because I'm rendering something inside of them, it will create fragments. Think of them like pixels that make up this space, right? Now I'm not going to draw them all, but these are each fragments. So the fragment shader runs on each one of these fragments here, all the way through the triangle. Fragment shaders are sometimes called pixel shaders for that reason. They're very much similar to pixels, and the reason we're calling them fragments is because sometimes OpenGL might decide that 2 pixels belong to the same fragment. There are other types of shaders, as I mentioned, so geometry shaders, tessellation shaders, compute shaders. You can see compute shaders requires OpenGL 4.3+. We have 4.1 because we want to support Mac OS. So we're not going to be able to use compute shaders, at least until we decide to deprecate Mac OS. But these are the shader types. You can read more about the rendering pipeline on the back end on this link here. So again, shaders take that vertex information from the VAO as input, and it outputs a color. So the vertex information from the VAO goes into the vertex shader. The vertex shader passes whatever it needs to pass through to the fragment shaders, and the fragment shaders are responsible for outputting a color for that fragment. You can have input come into shaders in 2 forms, so attributes, and if you remember that VAO call, GL vertex attrib pointer, that's important here. So it takes data in as attributes and data in as uniforms. So attributes tell OpenGL how to interpret the VBOs, right? So remember, I have these VBOs that define a vertex position, like this, for example. Let's take this one. So I have three floats that are a single vertex position, 3 floats that are a single color, and then the second one, right? The second vertex, the second color. So these 3, I need to expose that to the shader somehow. And that's what GL vertex attrib pointer does. We basically say, hey, we're going to take these 3 floats and we're going to store them in position 0. And on the shader side, we can read in position 0 as a vector 3, which is 3 floats, and then actually use that data. So you can see down here, this layout location equals 0 in vec3 position is exactly that. So we take data in with in. So in vec3 position is saying 3 floats. We'll call it position on the shader, and we give it this layout location equals 0 to tell it that it's in location 0. This will make a little more sense when you actually see the code. Ultimately, the important piece here is that this location ID maps to the attribute ID that we pass into this GL vertex attrib pointer call. So you can see, and this is probably the biggest takeaway, is that there's a very clear correlation between a mesh and a shader, right? If I have a mesh that defines a VAO with vertex positions and vertex colors, I need to use a shader that's going to take in vertex positions and vertex colors, right? And not expect there to be, for example, texture UVs, right? So the data that exists in a mesh needs to be properly exposed to a shader that can actually receive that data and expects that data, right? Nothing more, nothing less. So these are attributes. We also have uniforms, right? And uniforms are again, think variables, right? They're uploaded from the CPU, just like all of our other raw data that gets put into the GPU. Uniforms are just single variables that are uploaded to the CPU. The values persist across state changes, so once I set a uniform for a certain shader, it will be there until I change it again. But it allows us to pass in any data we want that isn't specific to a vertex, right? For example, I might want a transform matrix, right? So I have these 3 vertex positions, right? And they're defined in my VBO, but I might want to actually translate this thing all the way to the right, right? I could use a uniform to give it a matrix that will translate each vertex over here so that it ends up being rendered in the right place. And you'll actually see this is crucial. This is exactly how we're going to be able to move things around our world, is by passing in these matrices. And they're going to come in via uniforms. I can also have a uniform define a color, so I can tint the thing, right? So maybe my character is getting damaged, so he'll flash red a little bit. That can be passed in as a uniform, because again, it's not data specific to a vertex, it's not data specific to a fragment, it's just data that we want to expose to the shaders so that we can do something with them. And similar to the inlines on the shader side, we make these uniform lines. And uniform mat4 transform means that I can pass in a transform from the CPU, upload it to the GPU on the shader, and then we'll have that data available for us in the shader. Now, thinking through all of these things, the Hippo pipeline architecture is important, right? It's important to understand what it is we want to build and how we want to build it. There's a couple key points that I want out of this pipeline. I want to centralize and obfuscate direct OpenGL calls behind a renderer, right? I don't want to have a sprite class or a component on an entity to call OpenGL calls directly, right? I want everything behind the renderer. We want to have control over when rendering occurs and in what order we render things, right? And while doing that, also ensuring that we can consider if this can be made thread safe in an easy way, right? It doesn't mean we're going to prioritize thread safe at the beginning, but if it's all obfuscated in certain ways, we can actually ensure that when we make that step, it's a little easier for us. Now, when I say we want to have control over rendering and in what order, the order piece is really important, right? That's what gives us the flexibility in terms of sorting. So we can minimize texture swaps, context swaps, state swaps, right? What you'll see is I might have a sprite sheet, right? Or maybe not even a sprite sheet. Let's say this is my little character. That's its own texture. And then we have one where he's sort of jumping. That's a separate texture. Swapping between these textures often, sort of in between render calls, like that slows things down, right? To be efficient, we want to minimize that. So let's say I want to render this 20 times and this 20 times. I should render this one all 20 first, right? And then load this texture and render those 20, right? Instead of saying render this one here and then render this one here and then render this one back here, right? We don't want that back and forth, because the more you do that, the slower your pipeline is, and the slower you're taking, the more time you're taking to render that frame. So really, you want the textures to sort of be loaded once, render all the ones for that texture, and then you can swap the texture and render all the other ones. Additionally, the sorting is important, because if I have, let's say, parallax background, right? This is some mountains, right? Some really nice mountains. And then I have another one on top that is like bushes, right? Or like hills or whatever in the background. Obviously, the top part of this should be transparent, right? So if this is transparent, I want to be able to see the mountains in the background. The only way transparency is going to work is if the background is drawn before the foreground, right? Because the way transparency works in OpenGL is it just says, okay, take the current frame buffer, and if I have transparent pixels, just don't render them and render this on top, right? If I end up rendering the hills before the mountains, then the hill is going to be rendered, and obviously it's closer to the camera, right? So the hills will be rendered. This alpha pass will happen. It will find no mountains in the background, so it won't render them. Then it might render this behind it, but ultimately the Z position is further away, so it's going to be occluded by this foreground, even though the transparency is there. These are some of the intricacies about how to render transparency and how to deal with that sorting. So again, this sort of problem can be mitigated by ensuring that we can define our draw order, right? So all of these things, like all of these sorts of issues or performance concerns, can be addressed if we have flexibility over sorting the render calls in order to minimize those swaps. All of this, obviously, we want the API to be simple and easy to use, right? We don't want it to be difficult to use our renderer API. So here's what we're going to do. We're going to have a mesh class, which will handle the VAO, VBO, EBO setup with all the raw context or all the raw data that comes into a mesh, right? We'll have a shader class, which will handle shader program compilation and linking. So shaders like the vertex shader and the fragment shader, they're just like little programs, right? And you have to compile them and link them in OpenGL before you can start using them. We'll have a shader class that can handle all that for us. And then we'll have a render command class. The idea here is that we have a render command class that is subclassed when we want a different render command, right? For example, I might have render mesh. So I want render mesh to be a child of render command. It takes in the necessary data that it needs to take in. For example, the mesh and the shader, and then when somebody calls render mesh.execute, it will bind the mesh VAO, it'll bind the shader program, and then it'll call GLDraw arrays or GLDraw elements based on whether we're using elements rendering. So that would be sort of the way we would render any mesh. We'd be able to queue up this render mesh command and have it render the mesh and shader that we've passed in. All of this will be facilitated by a render manager class, right? So the render manager would have a queue of render commands. We would, as we're going through the frame, we would push these render commands to the queue with a submit method, and then we would be able to call flush on it for it to actually render all of the commands that it's received up to that point, right? So again, this is going to allow us, with separating the submission of render calls and the actual execution of them, will allow us to be very flexible in the future if we need to be able to submit, maybe we'll submit render calls from a different thread, right? And then we'll flush them all back on the main thread when we're ready. That sort of stuff, right? We're able to do that by setting it up this way. Additionally, we can have like multiple queues, like maybe for the transparency thing, maybe any transparent things need to go to their own queue, and then non-transparent things go to a different queue, because you might want the non-transparent things drawn first, so that the transparency, the alpha pass that happens afterwards, will capture them properly. We could even have a vector instead of a queue, so that we can sort the vector by Z position, right? So that's again the transparency piece there. Or again, sort on the texture, so that all of the things that have the same texture go first, and then we swap the texture and do all of the things that have the second texture. So this sort of thing. The render manager class will set everything up so that we can expand on it if we need to, based on any sort of performance impact that we might see. So that's it for today. Next video, we're going to build all this stuff, so definitely stay tuned, and I'll see you next time.